Good morning and welcome to the lecture series on numerical analysis. In this lecture, we will study about the interpolation and applications of finite differences to drive the interpolation formulas. Now, first we define what is the interpolation. So let yx be a given continuous function in some interval a to b and defined at n plus 1 distinct points x0, x1, xn such that these ordinates satisfy this condition. X0 is less than x1 is less than x2, xn is less than equals to b. Now these points may be equispaced or non-equispaced. It means the distance between the two consecutive ordinates may be equal or unequal. So graphically, we can see that suppose this point is our x0, and this point is x1, this point is x2, and suppose this is our xi point, and this is xi plus 1, and this is our second last point xn minus 1, and this is our last point xn equals to b. Now the distance may be equal between the consecutive coordinates or unequal. Now the problem of polynomial interpolation is to find a polynomial y and x of degree less than equals to n. As we know that if there are 2 points, then the degree of the polynomial passes through these 2 points may be 1. It means if we have 2 points, then the equation of the polynomial passes through these 2 points may be of degree 1. Similarly, here we are given n plus 1 data points, so degree of the polynomial either equals to n or less than n, so which fits the given distinct data exactly. It means y and xi equals to y of xi. Here y and xi is the derived polynomial, and y of xi is the exact polynomial, and I run from 0, 1 up to n. Such a polynomial is called the interpolating polynomial. So Newton's derived the interpolation formula for equal space points. It means distance between consecutive ordinates is equal. So suppose there are n plus 1 values x0, y0, x1, y1, xn, yn of x and y. It is required to find y and x. It means we do not know the exact behavior of the function y equals to fx, but we know the value of the function y equals to fx at n plus 1 discrete points. Now, a polynomial of degree n such that y and x agree at the tabulated points. Let the values of x be equidistant, this means equal spaced points. Xi equals to x0 plus ih, where I equals to 0, 1 up to n. Now, since y and x is a polynomial of n degree, so it may be written in this form: y and x equals to a0 plus a1 x minus x0. We start with the initial point x0 plus a2 x minus x0 x minus x1 plus and so on an times ax minus x0 x minus x1 up to x minus xn minus 1. Now, so this is our polynomial we have assumed, which is of degree n. Now, to here a0, a1, a2, and an are the unknown constant which we have to evaluate by using conditions. Now, imposing the condition that y and yx should agree at the set of tabulated values. It means this condition must be satisfied. It means y1 of at xi must be equals to y at xi. It means this is our calculated value, and this is the value of the exact value of the function at the point x equals to xi. So now, if we use this condition here, all right. Now, if we put x equals to x0, if we put x equals to x0 in this relation 1.1, then a0 plus a1 onward terms all are 0, because if we put x equals to x0, this goes to 0, this goes to 0, and this goes to 0. So we left with only one term, which is equals to a0. And yn at x0 is basically nothing but y at x0, which means y of y naught. So this is y naught equals to a0. So we find that a0 equals to y naught. This is our first constant term a0. Now, if we put x equals to x1 in this relation, then we find that yn at x1 is nothing but y1. A0, we know that this is equals to y0 plus a1 and this is x1 minus x0. And we know that x1 minus x0 is nothing but h, because distance between two ordinates. And a2 onwards, all the terms will be 0, because if you put x equals to x1, this goes to 0, this goes to 0. So we left only with two terms, a0 plus a1 times x1 minus x0. So if we simplify these terms, so we find that a1 equals to this is our y1. So y1 minus y0 divided by x1 minus x0. So this term is basically h, which is the step size of the interval, and y1 minus y0. Now here, if we use the definition of the back forward difference operator, so basically y1 minus y0 is basically del of y naught. Similarly, if we put x equals to x2 in this relation and simplify, then we find the value of a2, which is given by del 2 y0 upon h square upon 2 factorial. And in last, an equals to del of n y0 upon h ki power n upon n factorial. So till now we have derived the constants used in the equation 1.1. Now if we substitute x equals to x naught plus ph and substituting for a0, a1, a2, an, it means if we substitute these values a0, a1, a2, an in this relation at 1.1 and I put x equals to x0 plus ph, and if we simplify, then this equation 1.1 gives y and x equals to y0 plus p times of del y0 plus p into p minus 1 upon 2 factorial del 2 y0 plus p into p minus 1 times p minus 2 upon 3 factorial del q y0 plus and so on. Right? So because if you put a0 here, which is equals to y0, the first term is y0. Now a1 is nothing but del of y0 upon h. Now here x1 minus x0 equal, but x minus x0, from here x minus x0 is nothing but ph. So this is ph times of a1. If we multiply ph by a1, then we left with p times of del by 0. Similarly, you could simplify the remaining terms. Now this equation 1.2 is known as the Newton's forward difference interpolation formula. So which is very important formula, and this is very useful for interpolation near the beginning of the set of tabulated values. It means if we are given points x0, x1, xn up to xn, and we are interested to find the value of the interpolating polynomial at the starting of the table, it means either right to the x0, right to the x1, right to the x2, or left to the xn minus 1, xn minus 2, xn minus 3, and so on. So this formula is applicable when we are interested to find the interpolation near the beginning of the set of tabulated values. Right. Now, instead of assuming y and x as in 1.1, we start with the initial point x0. Now in place of x0 in this relation 1.1, instead of this point x0, if we start with the terminal point xn, then our relation becomes 1.2, which is given by y and x equals to a0 plus a1 times x minus xn plus a2 x minus xn, x minus xn minus 1, and so on. Now, again, then impose the conditions that y and x would agree at the tabulated points xn, xn minus 1, x1 upon x naught. We obtain after some simplification that y and x equals to yn. Now here, suppose we want to calculate this value a0. So put x equals to xn here. All right. So yn at xn is nothing but yn only. So this is a0. So a0 is basically yn, because if you put x equals to xn, then a1 onwards all the terms will be 0. Now if you put x equals to xn minus 1 in this relation, then third term onward all the terms will be 0. We left with only two terms. So from here, yn at x equals to xn minus 1 become, this is our yn minus 1 and this is our yn. So this is yn minus 1 minus yn upon xn minus 1 upon xn equals to a1. Now, if we use the backward difference operator definition, so this becomes p times of delta yn. And similarly, third term p plus p into p plus 1 upon 2 factorial enabler to yn, and so on. Here we are using backward difference operator because we are interested to find the interpolating polynomial near the end of the tabulated values. So where p equals to basically x minus x n upon h. This is our Newton's backward difference interpolation formula and useful for the interpolation near the end of the set of tabulated values. Now we see the application of these two formulas. So for example, find the cubic polynomial which takes the following values. So we are given x equals to 1, 3, 5, 7, corresponding values of the function yx equals to 24, 120, 336, and 720. Hence, or otherwise obtain the value of y8. It means outside the range of the given values. Now, first we form the difference table. So this is our first ordinates column, x equals to 1, 3, 5, 7, and this is our arguments values y equals to 24, 120, 336, and 720. Now first we find the first forward difference because we are interested to find the interpolating polynomial first, and then we find the value of the polynomial at x equals to 8. So we use Newton's forward formula here. So basically first forward difference is 96, 216, and 384. So this is, it means 120 minus 24 is basically 96. 336 minus 120 is equals to 216, and 720 minus 336 equals to 384. Similarly, second forward differences can be obtained by the consecutive first forward differences. It means 216 minus 96 is equals to 120, and 384 minus 216 is equals to 168. Now the third forward difference is basically 48, which is a difference of 168 and 120. Now here that the distance between the consecutive ordinates is 2. Difference between 1, 3, 5, and 7 is equal, which is equals to 2. Now if we assume x0 equals to 1, first initially starting with the point 1, then we have x equals to 1 plus 2p because here step size is 2 and we then x equals to x0 plus ih, right? And h equals to 2, so x equals to 1 plus 2p, so p equals to x minus 1 upon 2. Now substitute this value of p in the fourth Newton's forward difference formula, which is given by equation 1.2. Then we obtain this relation yx equals to y0 plus p times of del y0, and here p equals to x minus 1 upon 2, and this is p into p minus 1 upon 2 factorial. So p means x minus 1 upon 2, x minus 1 upon 2 minus 1 upon 2 factorial del to y0 plus, and so on. So here we have only table up to third forward difference here. So we use on Newton's forward difference formula up to the third forward differences only, because higher differences are not useful for us. Now, if you substitute the values, corresponding values of ordinates and corresponding forward differences. So y0 is here 24. So we put y0 equals to 24. Del of y0, del to y0, del to y0 basically are the first entries of these columns. So this is our x0, this is our y0, this is our del of y0, this is our del to y0, and this is our del cube y0. Now substitute these values in this relation and simplify, then we get the third degree polynomial x cube plus 6x square plus 11x plus 6. Now this is our third degree polynomial which passes through these 4 points. Now we are interested to find the value of the function at y equals to 8. It means if you put x equals to 8 in this relation and simplify, then we get y8 equals to 990. Now, interesting to note here that this process of finding the values of y for some values of x outside the given range is called the interpolation. It means interpolation means values of the function in between the given data points. Extrapolation means values of the function outside the given data points. So this problem was based on extrapolation. Now next we see one more example, which is the application of the Newton's forward as well as backwards formulas. So here we are given the values of x at between 0.10 up to 0.30, and the corresponding values of y are given. So we have to find the value of the 10 at 0.12 and 10 at 0.26. So here 0.12 lies between 0.10 and 0.15. So it means we are interested to find the value of the function at the starting of the tabulated values. So we use Newton's forward formula here for the first case. While in the second case, 10 at 0.26, 0.2 slides between 0.25 and 0.30. It means we use Newton's backward formula to find the values of this 10 at 0.26. So we form the difference table here. X equals to 0.10, 0.15 up to 0.30. This is the value of the function. Y equals to 0.1003 and so on. So now first forward differences, corresponding backward differences. Now first forward difference, it means this minus this, 0.1511 minus 0.1003 is basically 0.0508. Similarly, for first forward difference equals to this one, this one, this one. So these are the first forward differences. Similarly, the second forward differences, it means differences of consecutive first forward differences. It means this minus this equals to 0.0008. Similarly, second forward difference, and this is our last second forward difference. Similarly, we find third forward differences and fourth forward differences. Now, to find the value of 10 at 0.12, so we assume that x0 equals to 0.10. Then, so x equals to x0 plus ph. So here x equals to 0.2 because we are interested to find the value of 10 at 0.12. So put x equals to 0.12, x0 is equals to 0.10 plus p times h. Now here see that the data points are equally spaced and space is 0.05. So h equals to 0.05. So from here we find that p equals to 0.4. Hence Newton's forward difference interpolation formula, which was given by 1.2, gives this relation. So this is interesting to here note that we obtained the fourth forward differences up to. So we use Newton's forward interpolation formula up to fourth forward differences only. So this is our Newton's forward difference interpolation formula. So we put the values of corresponding y0, del y0, del 2 y0, del q y0, del 4 y0. So basically, which are the values at the top of the columns. This is our x0, y0, del y0, del 2 y0, del q y0, del 4 y0. And if we simplify, then we obtain the value 0.1205. Now next we find the value of 10 at 0.26, which is at the end of the table. So we use Newton's backward formula here. So we have x equals to 0.26, xn equals to, it means end value of the table. It means this is our xn here in case of Newton's backward formula. So this is our xn, this is our yn. So this is our 0.26 equals to 0.30 plus p times of 0.05. So it gives p equals to minus times of 0.8. So hence Newton's backward difference formula is given by this relation up to 4 backward differences. Now we use the bottom values of the corresponding columns. Yn is the bottom value of the second column. Del nebula of yn is the bottom value of the third column. Nebula 2 yn is the bottom value of the fourth column. Nebula q yn equals to bottom value of the fifth column, and nebula 4 yn is the bottom value of the sixth column. All right. Now, if we simplify, then we get the value at 10 equal 0.26 equals to 0.2662. We see one more example. The following are the number of deaths in 4 successive 10 years age group. Find the number of deaths at age between 45 to 50 and 50 to 55. So here we are given age group 25 to 35, 35 to 45, 45 to 55, and 55 to 65, and the number of deaths between the age groups. Now first we find the difference table. So now age up to X. It means in this one 25 to 35. So age up to 35, 45, 55, and 65. We take the maximum age in the range. So 25 to 35, the maximum age 35. So we take here 35. 35 to 45, so we have take 45. 45 to 55, so 55, and 55 to 65, 65. Now number of deaths. In this range, 25 to 35 is number of deaths equals to 13229. Now, age up to 45, so number of deaths will be this plus this. It means 132229 plus 18139, which is equals to 31368. Number of deaths at the age up to 55 will be the summation of these three entries, which is given by 55593. And the age number of deaths at the age of up to 65, which is given by the summation of all these four entries, which is given by 87089. Now we find differences. The first forward difference is given by the consecutive differences of the arguments. It means 31368 minus 13229 is given equals to 18139. Similarly, this minus this equals to 24225, and this minus this one equals to 31496. Now the second forward difference is the consecutive differences of the first forward differences. It means this minus this equals to 6086, and this minus this equals to 7271. Third difference is 1185. Now here you could see that the given ordinates are equally spaced, and here h equals to 10, age group of 10 years. Now if we assume x0 equals to 35 here, x0 equals to 35, so p equals to x minus x0 upon h, so x equals to 50, because we are interested to find the number of deaths at the age group between 45 to 50 and 50 to 55. So here 50 is common. So we will find the value of number of deaths at the age of 50 up to 50. All right. So x equals to 50 here. So 50 minus 30 forward difference formula 1.2, we have y0 plus p del y0 del 2 y0 del q y0, because we have only third forward difference terms. The remaining terms are not required. So now if we would put p equals to 1.5 and the corresponding values of y0 and forward differences. So this is our y0, this is our del of y0, this is our del 2 y0, del q y0. And if we simplify, then we get 4264, the number of deaths at the age up to 50. Now, death at the age between 45 to 50 is nothing but number of deaths at the age of 50 minus number of deaths at the age of 45, which is, it means 42646 minus number of deaths at the age up to 45 is 31368, 31368, which is equals to 11278. So these are the number of deaths in the age group 45 to 50. Now death at the age between 50 to 55, it means number of deaths at the age up to 55 minus number of deaths at the age up to 50. So this is at the 55, number of deaths at the age up to 55 is 55593 minus 42646, which equals to 12947. So thank you for today.